Now, this is a somewhat different kind of video I'm trying here, and I'm gonna start this off with an invitation and a warning. First, the warning. I've already made a video about Fermi question. again, Fermi questions and Vogel exercises, but the video was bloated already and I couldn't fit in an actually worked through example of a Vogel exercise, so I'm trying to do this here. This means that this video will be much more technical and have much more math in it, and it will be more hands-on. That's why it's called a hands-on video. Not super sure how it's gonna turn out, so please let me know. Still, I feel it can be interesting for a more general audience because I will try to make it kind of a guided tour to show you how a bit more complicated things that you didn't come into contact with in high school can be solved and can be calculated. Also, I'm going to try to interject some more conceptual bits. Hello there and welcome to Context Corner. Whenever you'll be seeing me talking here, I'll be trying to give you a context view and just a broad overview of things. So even if you cannot follow all the mathematical details or don't even care to, I think I can still give you the overall flavor. Right, let's dig in. Let's start with the problem description. Exercise: to the edge of the universe. In a science fiction story, the hero finds himself on some sort of belt on which he can only tentatively move at around 1 meter per second. Soon he realizes that of the two ends, A and B of the belt, and A is being held in a fixed position. The other end, B, is being pulled away at 10 meters per second. Luckily, the material of the belt is elastic and arbitrarily stretchable. Initially starting at A, can our hero ever reach end B of the initially 1 kilometer long conveyor belt? And if so, how long does it take? The edge of the universe, currently around 2 times 10 to the 10 light years away, is rushing away from us at the speed of light. Assuming the usual geometry would apply everywhere in the universe, when would a rocket going c-half catch up with it? If you are able to do this kind of math, so calculus and differential equations, then give it a go. Pause the video here and try to do it yourself and then come back. And all the others, just keep watching. So looking at the exercise, this is some form of kinematic problem where we are given some distances and speeds and have to calculate the details of the motion. First order of business is to define our coordinate system in a way that is practical and useful. And the most obvious part is to define the origin of our system at the point where the person is starting, so at the fixed point A, and have it pointing in the direction where the belt is being stretched, so towards point B. This is just a one-dimensional problem, so we'll call this the x direction and we're done. Consequently, x of t will denote the position of the hero along the belt, and x dot of t will be his velocity measured towards point A, so towards the fixed point. And that's already where we're going to start formulating the first equation. The velocity of the person, of the guy, has two components. First, his own movement on the belt, which is a constant that was given, and I'll just call it u. And secondly, because the belt is stretching between the 2 points, it will elongate and also carry the person standing on the belt forward. And this speed I will call v. So we have our first equation, x dot is equal to u plus v. We've already stated that u will be constant, but v will grow in proportion to where the person is standing on the belt. So for example, if it's standing at the midpoint, then he will be traveling at half speed of the endpoint, and so on and so on. So this means we can equate the proportion of his position to the entire length of the belt to the same proportion of his speed component v to the total speed of the end of the belt. Defining the total length of the belt to be big L and the speed at which the end of the belt travels as big V, we can write this down as x over big L is the same as v over big V. Or put differently, v is equal to x over big L times big V. Big V is a constant known to us, but big L is growing bigger and bigger over time. So the length of the belt is growing because one end is always moving away. We can formulate this as saying big L of t is equal to L0 plus big V times t, with L0 being the initial length of the belt and t being time. This expression just means that we have an initial length, and this one is growing bigger and bigger linearly with time because the end of the belt is moving away with a constant velocity. We can plug this into the equation we already have to get v is equal to x times big V divided by altogether L0 plus big V times t. At this point we're going to introduce a new variable called lambda, and we will define this as L0 over big V. This will allow us to further simplify the equation we have to v is equal to x over lambda plus t. First order of business, this new variable lambda that we introduced, it doesn't have an important physical meaning. It's just there to make it more simple and easier to handle. So that was a lot of work already, and we can come back to our very first equation of the velocities and put in all the equations we found. This will give us x dot is equal to u plus x over lambda plus t, or arranged differently in terms of the variable x dot minus 1 over lambda plus t times x is equal to u. And this is a good time to take stock and take a step back and see what we have achieved so far and what our next step will have to be. We have managed to put all of our initial information into a single equation and have this single equation completely describe the motion of the person in question. So all we have to do now is solve this equation, and then we will have the full information we desire. Unfortunately, the equation that we got is a so-called differential equation, meaning that it does not only contain our variable x, but also derivatives of this variable. So in this case, a first derivative. This is of course not a coincidence, but extremely common in these kinds of kinematic problems, because there is this simple hierarchy that you have the description of position, which is mostly called x, and then you have the rate of change of position will give you the speed, which is equal to, in mathematical terms, which is equal to the first derivative. Next, the first derivative of the velocity is the acceleration, meaning the acceleration is the second derivative of the position. So you have this simple connection between the different kinematic expressions, and these will in almost all cases lead to a differential equation. Solving a differential equation is unfortunately really difficult, and in many cases even impossible. There is not one single way to do it, but there are many different approaches that you can try, very similar to integration. So to get an idea of what to do next, we'll take a closer look at what type of differential equation we have, and this will inform our next step. So first up, it is a first order equation, meaning that it contains only the first derivative and nothing worse. It is also linear, meaning that all the expressions of x, so x and x dot, are just in linear form and not squared or within a root or something even worse. And lastly, we have an inhomogeneous differential equation. because when arranged so that all x terms are on one side, there is still another term on the other side. It's not equal to 0. Altogether, this determines our strategy, which is that we first solve the homogeneous equation and then do a variation of constants to find a solution to the actual inhomogeneous equation. Now that we have the homogeneous equation, we can solve it directly by integrating. In order to do that, we'll just have to write x dot as dx over dt. And then we rearrange terms so that on each side of the equation we only have one variable. And this will look like this. Dx over x is equal to dt over lambda plus t. This is called the separation of variables for obvious reasons. Now, given in this form, we can rather straightforwardly integrate the equation on both sides, meaning we get an integration constant c. It's actually more convenient at that point to write the integration constant as ln c, because then we can use the logarithm rules to simplify the expression and simply solve to get x of t is equal to big C times lambda plus t. So that's the simple expression we got there. But remember, we've only solved the homogeneous equation yet. And to solve the inhomogeneous equation, we need to do something called the variation of constants. To solve the actual inhomogeneous equation, we will treat the integration constant c as a function of t. So we shall replace c with c of t. So x of t is equal to c of t, now treating the constant as a variable, times lambda plus t. Which means if we differentiate it, we get x dot of t is equal to c dot of t times lambda plus t plus c of t times 1. If we now take this expression and substitute it back into the original differential equation, we get an equation that we can again directly solve. C dot of t is equal to u over lambda plus t. Integrating this again directly gives us c of t is equal to u times ln of lambda plus t plus a new constant k. Note that as we did another integration, we got another integration constant, and this time we call it k. And to fix this, we're using the information we have about the movement of our hero, meaning his position at the beginning of the motion is at point 0. He's starting at the fixed point A. In terms of this formula, it means that x of at time 0, so x of 0, is equal to 0. This quickly gives k is equal to minus ln of lambda. And the entire solution can now be simplified to x of t is equal to u times lambda plus t times ln of lambda plus t divided by lambda. And that's the entire solution we were looking for. We now have a function describing the position of our hero at any given point in time. Meaning for every point in time we can completely and directly calculate his position. Alright, so now we have access to all the details of the motion, and this means we should be able to answer all the questions. So the actual question was whether the hero standing at A moving towards B can ever catch up with end B. We've already formulated an expression for the position of B at any time, which is just the length of the belt big L of t. And now we know the position of the person at any given point. So if we just equate these two, we can calculate the point in time when they meet, when they are equal. As a quick reminder, we had big L of t is equal to L0 plus big V times t. And we set this equal to the expression of x of t that we just calculated. Therefore, u times lambda plus t times ln of lambda plus t divided by lambda is set equal to L0 plus big V times t. Despite the way this looks, it's just a regular equation, and we can solve it just like any other regular equation. So quickly, this yields that t is equal to lambda times e to the big V over U minus 1. We already know all the numbers, we already know all the speeds and distances, and we can just put those in, and this will give us a time of around 2 times 10 to the 7 seconds, which is in a different time scale, more useful time scale, it's about a month. Now, what about this result? It is obviously way more than the person would need to run just to the undeformed belt. But the main point, the main interesting result we get is that we get a solution at all. It's quite counterintuitive that the guy moving just 1 meter per second can catch up with the end of the belt, which is moving away at 10 times that speed, 10 meters per second. Intuitively, I think we would say he could never catch up, but what we miss here is the speed components that the guy gets from being on an elongated belt. So while the end of the belt might be moving away really fast, this also means that the belt transfers some passive velocity to the person standing on it, making him faster all the time, even if he's just moving very slowly. This means that the speed of the person on the belt is increasing very slowly, very, very slowly, but is always increasing and will finally be high enough to catch up with the end of the belt. But wait, there was a second part of the question, wasn't there? The edge of the universe, currently around 2 times 10 to the 10 light years away, is rushing away from us at the speed of light. Assuming the usual geometry would apply everywhere in the universe, when would a rocket going c-half catch up with it? At first glance, the good question is, what does this have to do with the first part of the question? And is this a copy and paste error or something? It looks like a total non sequitur. However, if you think about it, our belt model is just a simple description of the expanding universe, where objects can move within space and are carried along by space. And therefore, just like the person on foot on the belt, the rocket chasing the end of the universe can catch up with it. And the reason is the same. Apart from the own velocity of the moving subject, there's also the passive velocity you get from being within or on a stretched object. And this velocity is increasing, ever more increasing. The further along the belt or the universe you get, the bigger this velocity component gets. So if we put in all the numbers, we get quite an astronomical result of 10 to the 11 years. If this means nothing to you, it's about 10,000 times the age of our universe. So while technically you could catch up, it's very questionable if you get this amount of time in the universe at all. And even more technically, even if you're traveling on foot through the universe, so with a speed of 1 meter per second, you could also catch up with the end of the universe flying away at light speed. But this will take you even longer. And that's a number you can only express as 10 to the 10 to the some number. So it's really, really up there. Of course, we have to acknowledge that we used an extremely simplified model here. So we completely disregarded the curvature of space, or we rather assumed that it is completely flat at any point in space. And also that we were not calculating relativistically, even though in the second part of the exercise we had objects moving at light speed or half light speed, so we clearly would have to use the special relativity equations here. But that's kind of beside the point. Of course, this is super simplified, but it's very instructive to understand the simple fact: when something is stretched and you are in it or on it, then this stretching means that it carries you along as well. So you do not only have to respect your own velocity, but also the indirect, the passive velocity you get just because from being carried along with it. This simple idea is really what this entire exercise was about.